right, so thank you very much. Really nice that so many people are still in the late afternoon after cake and coffee still here. So, as Marie said, my name is Simon, or Simon actually. I'm the CEO and co-founder of FRANKA EMIKA. We are a robotics startup here in Munich, in Schwabing actually. I'm going to try to, in the next 40-45 minutes, show you what the new possibilities in robotics are, and with a focus on, it is the subtitle of this talk, the art of manipulation. And I'm not talking about manipulating you and your thoughts. We're talking about manipulating the physical world, so interacting with the real world, because that is actually something quite new that is now being more and more introduced into research world, but also into more application world. I'm going to try to give you a quick overview of where is robotics now and where is it going to go in the next years. And I'm going to start with the very first picture. For us, robotics, or for everyone, robotics should be or has one single purpose, and that is to safely support you or us, all humans, in whatever task it is we're doing. And we want that because we want to be relieved of dangerous tasks, of monotonous tasks, and of tedious tasks. And we see robotics to be one day in the history books in the line with those really fundamental breakthroughs in technology. In Germany, there's a very, very big, let's say, word or group. It's called Industry 4.0. I guess most of you have heard about it. But for us, robotics is much more than industrial applications, because basically, when we talk about robotics, we're basically talking about the so-called cyber-physical systems, so those systems which will connect the internet to the real world. And I think that's, we're on the verge of that right now, and narrowing that down to industrial applications, I don't think is the purpose of it. But what is the reality? The reality looks like that. Millions, hundreds of millions of people actually, every day go to work and are exposed to danger, whether that is hanging down, top down from a 200 meter or 300 or 400 meters high building, going to work, doing the same task, pushing buttons. I mean, these are real photos from iPhone factory, where millions of people are, their task is to push a button, to insert a cable, to test an app. Or we have those people, especially in our countries also, that follow real dangerous tasks, so interacting with sharp objects, with poisonous objects. And why is it that we don't have the technology, or why aren't there robots doing those tasks? Because robotics is, or has still, or used to have, now not anymore, fundamental problems. And the first fundamental problem is the usability. Who can actually use a robot? Those are usually guys that have a technical background, whether that is an engineering degree or something equivalent, and then are trained on robotic systems. And then you're able to install a robot within, let's say, weeks or months, that it actually does something. And it's not just a machine standing around. From that, we have the second problem. There's only a very small group of people you can actually hire to program your robot. And those people are usually quite expensive. So we reach that point where robotics is not affordable anymore. Or basically, when we see who is actually using robots today, it's to almost 95% automotive industry, whether that is the car manufacturers themselves or the suppliers of the car manufacturing. And why is that? Basically, the reason is because they're building the same car body for 10 years or 15 years or 20 years, and then you can afford to set up a robot for months or even, yeah, I wouldn't say years, but it can take quite some time. As we just heard from the Tesla manufacturing, it's not so simple to introduce robotics. And that basically means we have zero scalability. On the one hand, because it is quite expensive. On the other hand, once you actually program the robot, let's say a welding robot, which is the typical task, welding, point welding, when you want to copy that to a second robot, it is not really possible. You have to start every time from scratch, more or less. And the fourth problem, and that's actually what I mostly want to focus on, is the functionality. So what can robots actually do? Whether that is Pepper that you see out here standing around, or industrial machines. They are so-called positioning machines. That means everything is pre-planned with motion planners, a lot of work put in there. But everything, and now comes the big kicker, everything that requires contact, so meaning interacting with the real world, it's just not possible. Why is that not possible? because they're positioning machines, driving from A to B, and they do that for the next 100 years, but once they need to interact with something, they can't, because they don't have any sensors to measure physical contact. And that's why industries look like this. We have basically two universes. We have automation manufacturing, where robots are by themselves, and we have those manual tasks. The degree of automation is much less than most people think. The highest automated company, or the former highest automated company, because I'm going to show you later on some quick clip from our production, is a car manufacturing company from Stuttgart, and they reach roughly 25% of automation in the entire production or manufacturing of the cars. And those are basically the tasks that are manufactured. It's welding of the car body and painting, which we do not see here, but these are the two main cases that are actually happening in the world. Now, my background is actually from DLR, it's the German Aerospace Center, so basically the German NASA. And what happened there was the development of a new type of robot. It began in the late 80s, where our former boss, Professor Hitzinger, and another colleague had the idea to support astronauts in space, basically. But the problem, or because, I mean, astronauts leave the ISS for opening a lever, but they put on for 3 hours an astronaut suit, and then they go out for 2 minutes and they come back in. So the idea was obviously to support them. And the problem was, though, that there is no robot that can give you a force feedback, basically. So did you actually turn the lever? You could not give this response. So the idea was to create a robotic system that has some sort of force feedback. And the first application, what we actually see, what you see in those videos is now copying human abilities. And human ability is behavior. So we can suddenly create not only a position, a stiff motion, what we can do now is to make the robot compliant, or you can make him stiff. And all that by control. And the problem that actually arose from that, or from this video, was one of the first videos that showed a robot and a person in the same workspace, right? So for some reason, this video is, by the way, from 2006, and this young man is my brother, and I was filming during night time because we were not sure what's going to happen. And that is actually the question, is this safe? This became a much more prominent topic than we ever thought of, and by now we talk about something in German, it's called MRK, Mensch-Roboter-Kollaboration, or human-robot interaction, which became somehow, so under the title of cobots, the main issue. So is this safe or not? But the idea was never just to make a fenceless robot, but the idea was to create a system that is capable of more things, and not just to remove the safety fences. But obviously that is a very critical thing. So what was the next step? The next step was to introduce robot reflexes. So when you put your hand on a hot plate, you do not need any higher computational power in your brain to remove your hand, but you just do it. It's a very rudimentary reflex we have. This is a spinal reflex. So without you thinking about it, you're going to remove your hand. And basically that is what was introduced into robotics. This is the so-called collision detection. And what we see here are now high-speed collisions, so roughly 2 meters per second, or even low-speed with a knife. So we drove here with 0.75 meters per second, and my brother's arm is still functional, more or less. So this was the next. I mean, copying biology is usually quite useful. So, and what we did then, as he's a professor, by the way, so maybe it shook the right synapses. No, so the second step was then from a single lab test, obviously, to large-scale testing, similar in the car manufacturing industry. So we did thousands of experiments trying to show that those types of robots, if they have this type of sensitivity, they can be used without any safety guards because they are inherently safe. And the entire industry is now, this is a major topic actually, and a lot of robot manufacturers started to kind of use that, but this is what you're going to see now when they try to introduce collision detection into a robot, because it's actually not that difficult. But the problem is the robot itself, and that's what you see up there. Can we make sound? It's a really nice sound, actually. I saw it somewhere here, right? No? Ah, okay. So you can imagine it's really loud when it hits hits the person. And the second step then was using volunteers, what we see here actually. So it was back in the days at DLR, right? We were allowed to do stuff like that. So what we did here, what you see is really fast motion, actually 2.5 meters per second, which is an unbelievably fast velocity for a robot. And after that, we brought the volunteers into the university clinic, which is not so far away from here, and checked, not because they were injured, but we wanted to do MRI scans, so to see whether there was any injury or not. And we could not detect any injury on these cases. Okay, so what I initially quickly said is collision detection is not that difficult. Actually, what you do, you just compare your input with your output, right? And all robots are basically, this is basically a joint which has a motor which gets a power, and you have a current sensor on the antriebsseitig. So before in front of the motor basically. And when it collides with something, an energy is detected, a peak, which is then different to what I put into the machine. And that's how I know something collided with the machine. But the idea, as I said, is it was never the idea just to introduce collision detection as a binary function, so whether yes or no, because then it would mean your robot would just stop all the time. So what we did is actually to develop a torque sensor, so a real measurement of the real external torques and external forces, and put it on the far side of the motor, so we can measure the real external forces and external torques. And why do we do that? Is what you see here. So basically, and this is now where learning and all big words that are thrown around these days come into play. So all we do in the end is basically have a torque profile over time, right? Because we tried modeling these situations, modeling all kinds of different situations so that the robot would understand somehow whether this is a wanted collision or an unwanted collision. But it was almost hopeless, so we tried with experiments. So data-driven, collecting torque data, collision versus interaction. So the machine understands whether it is a wanted or an unwanted collision. And then I show you the first experiment of such kind. So the robot understood now that Saskia was grabbing him with the hand. And now he understood that it was not an intentional collision. And this is, let's say, the second generation of differentiating collisions. And later I'm going to show you, because manipulation, interacting with the physical world, is a constant collision. But the robot needs to understand whether this is wanted or unwanted. Let's say he's used in an assembly task, right? Putting together a computer. It's constantly colliding, but he needs to understand this is on purpose. And I'm going to come back to this point in a second. No, it's stopped. So this is our robot, which we developed over the past 6 years. We started mass production in last November. And as Marie said, we had been very gracious with awards from the German federal president of this country, but also in the US, Popular Science or Edison's Award, because what I'm going to show you in a couple of seconds is quite a breakthrough in robotics. So what are the key features actually of the system? First of all, the usability. So what you see there on the right side, you don't write any lines of code anymore. What we did, we introduced something everybody knows from the internet world or from classical IT, is a hardware abstraction layer. So you do not need to write any codes anymore, but we created skills and apps which bundle functionalities, and in the end you just drag them into your timeline and push play. So what we see here is here on this side, all the apps that are just on your smartphone installed on this very robot. Here you have those timelines that you do up here. So this is the timeline where you put all your apps together, and this is where you can store them. And what we see here, for instance, is the programming from one of our major cases is iPhone quality control, and that's what you see there. So these functionalities is basically interacting with the person, opening the smartphone with pushing the home button, opening the smartphone, putting a calculation into the calculator, and closing the iPhone again. It's a typical end-of-line testing of a produced or manufactured electronic device. So you don't need any special skills anymore to program a robot. And we actually did we opened up an academy at our place where we invite basically everyone who's interested, who has never programmed or who has experience in robotics. And we have even school children from 8 years old. And we did a statistical analysis, and what we figured out is that 7th graders are now only 20% slower than a postdoc in robotics in programming this robot. Where we actually, and that's only the relative time, right? Where we actually reduced the absolute time from weeks or months to minutes. 2 weeks ago or 3 weeks ago at Hannover Messe, we basically made a live setup of the robot. It arrived from an Amazon delivery and it came to me. And together with our Minister of Digitalization, Frau Beer, she was actually able to set up everything within 5 minutes with an audience, similar crowd like this, even though she was sweating and red, but it somehow worked. Second thing is what you can do now is multi-robot deployment. So once you actually did this, you created the task on one robot, what you can do now is basically through a cloud system, deploy your tasks on one robot, on 5 robots, or 5,000 robots without any extra effort. So basically drag and drop, copy, paste what we know from the IT industries. And here I show you a couple of cool features of it's a bit older prototype, but was still functioning. And what we see here are something called virtual walls. So what we can introduce now is we give the robot spaces where he's not allowed to go into, even though you throw him into. Basically he bounces back, what you see now, because for instance you don't want the robot to destroy the screen, right? So you put a virtual wall. Another thing is the sensitivity. What we actually see here on the video below is with a nail driving into a balloon, and the balloon does not burst because the robot stops that fast. And that is one of the most critical things which a lot of, let's say, stakeholders that are all going into robotics, because robotics is quite, let's say, a hot topic now. The problem we have with real machines is that real time in robotics does not mean, I saw before at Oculus we have 90 frames per second or something, but we were talking in kilohertz at least, so 1,000 signals per second, right? And why do we need that? It's because the human has, what I showed you before, the spinal reflex to protect myself. It needs 80 to 100 milliseconds until I can actually react to a danger. That means your machine must protect you in that delta time. Otherwise, it's no meaning because the human could react already. So if we would, and now comes the complicated part or the tricky part is, let's say we connect all these robots to some cloud or something. The problem is still the latencies. You cannot use any cloud connection till today which will give you any kind of information for the time you need it to react, because we are talking about different digits of velocity or frequency we actually need here. And as I said, here was a prototype, and now I'm going to show you a cool video of super sensitivity. So the balloon, this is because this is our newest version. Yeah, it still works, but what we can do now, we can blow against the robot, or we can even throw the balloon against the robot. And the sensitivity is so strong that it even feels single grams of contact. And what is it? Why is this even possible? We have in each joint, so in all these 7 joints, we have something called torque sensor, which is nothing else but when you take your finger and you overextend it, then you have torque sensors basically in your muscle tendons. That's how your body realizes that you are using that or overextending that finger. And that's the same what we introduced now into robotics. And what is it you can actually do now? That's where we come into the nice videos now. We can learn manipulation. So what we see here now is a typical robotics problem. Sorry for the videos are sometimes a bit strange because I have a new laptop and I did everything on Apple and you know how it is. So this is peg and hole, right? So inserting something that is quite difficult to insert a peg into a hole. And you see the human needs a couple of seconds for each of those. And what we see here now is that robot is testing itself. Nobody programmed that robot. The robot is trying to complete this task by himself. And what you see is now at the 12th trial, he's already managing. At the 26th trial, he's getting a bit faster. And at the 43rd trial, I think he's going to manage now really fast. Yeah. And that is actually industrial qualities. So we can, without anyone ever programming this robot, do insertion tasks now without programming them. And then, because now it comes this question of strong and weak AI. I'm not sure, maybe everybody knows, but weak AI basically means I have, let's say, face recognition, and I solve that, and I can recognize faces, but to transfer that knowledge to a different problem, even a similar problem, is still very, very difficult, very far away from actually happening. But in this case, what we could do, what you see now is that the robot tried to insert that peg, and what we did now with the prior knowledge to insert the other pegs, which is a totally different problem for the robot. It's completely 100% opposite. But he does not need 43 trials anymore. Now he only needs, I don't remember, I think 11 or something. And he gets faster than actually a human. We did the very first experiment of that roughly 10 years ago. So the hand you saw initially. 10 years ago, we did that the first time. And the human was back then the son of our boss. And he was, I think, 6 years old or something. And he was way faster than the robot. The robot took almost 2 hours for this problem, and the son in a couple of minutes. So the hand you just saw, we did a real trial now. He's now 16 roughly, and we used our new robot. And what we see now is that the robot, and we see it especially in this last example now, where he uses, again, prior knowledge, he basically needs no more retrials to execute that task. And that is pretty cool, to be honest. So when you have a machine of such kind that is capable of learning manipulation, so without any programming of anyone, he can just try it out himself. What is it you actually get? You get a multifunctional tool in the end, which can do things for you that where you maybe even have no idea how to do them, but he can try to solve them. And that is the opposite of what is automation today. Automation today is 100% special solutions. So everything is a single application, and there's no way to transfer that knowledge on a new problem. And I'm going to show you a couple of quick videos. So what we see here now is a quite famous DJ demo, where a robot is using a DJ panel, but what he's actually doing again is end-of-line testing of an electronic device. And what you see is that we have no extra end effectors on, no cameras or no nothing. It's just the sensitivity of the robot enables him basically as you would. I'm not sure if there's an after party after this conference, but if there is, you all know when you get home and you're a bit tipsy and it's dark and you're trying to put the key in the lock, right? And you don't see anything, you will still manage it. And that's what we're doing here. Basically, it's the exact same thing. And, sorry. How am I in the time? It's fine, right? I'm going to jump a little bit here through this video. Okay. This is maybe important to see. So what you see now, the colleague just moved that little tray. And for a normal robot, it would be impossible to execute the task. But look at what he's doing now. Just like you would do it, right? You're trying, we call it wiggling. So you wiggle in the piece of the workpiece into the target area. And the same accounts for a CNC machine. Without any, so we can use tolerances. So the world is filled with tolerances, because everything is not at the same place all the time. And then we can solve problems like this, computer assembly, which is 100% manual labor, mostly in the far east of this planet. And what we see is that the robot, or single robot, can remove the dummy, insert the real CPU, close the lid, right? And we do this blind. That's very important to understand. That's why I'm calling it the art of manipulation. So we are heavily engaged into learning that the robot without any eyes can solve many, many problems. And what you see now, he puts the cooler on top, and the second robot comes now with a screwdriver and will fix the screws, I think. Should. So the other one pushed it a bit into its press fit, and then the other one comes, and you see he's trying to screw those screws, but not in a single way, because he understood that when he inserts the first screw, then he will not manage to put in the other screw. So that's how he learns, basically, to get better at these tasks. And I can jump a little bit. So this is what I showed you before, right? iPhone testing. So in this case, for instance, the robot is doing a selfie of himself. Right? Opening the camera, putting the front camera, take a photo, right? So it's the new selfie stick. You have a robot. And this I show you because I told you in the end I'm going to give you a quick sneak preview into our own production. These are some of those cases. But in the end, so these are our control boxes, so our control computers basically being assembled. So this was at Hannover Fair last year. And here basically the robots are assembling their own computers, right? Here I show you a quick how is actually the interaction with the robot. So you basically show him a couple of process parameters. This is again from smartphone production, so end-of-line packaging. And within a couple of seconds, of course, this was also at a fair, so it's accelerated a little bit by 1.5 factor, but you could do this also in reality that fast. And now, without any programming, the robot was able to do these tasks. So you only put together some of those. You see that here, where basically the line is going through all the functionalities he has to do, right? And then once you pack the smartphone, you want to pack it again to ship it with Amazon Prime. And what you see now is everybody knows pick and place for some reason. And what we do now here is pick and place, but now what we call sensitive sorting, right? And what you see now is how would this robot now put this together, and he is doing it just the way we do it, right? So without any cameras, it's very important because, as you know, everybody knows the problem of bin picking combined with some sort of perception sensor. It's still a mess, to be honest, but someday I hope it's going to be solved. And now I'm going to show you a couple of sneak peeks from our manufacturing. So this was a prototypical implementation of assembling the joints, or assembling the robot actually. And on the right side, this is our manufacturing line. And what we see now is we're targeting, as I told you, Daimler, car manufacturer from Stuttgart, have 25% automation. And what we're talking about here is almost 80% automation. And why is that critical? It's critical because our robot is not manufactured in China or something. It's manufactured roughly 80 kilometers away from here in a former Siemens factory, which they left because all electronics manufacturers are leaving this country because they're saying it's too expensive. But if you now, with a few people and a lot of robots, which cost 10,000 euros, you can suddenly manufacture electronics in Germany again. And I think this is, for us, almost one of the most critical things that we are capable to go into competition with low-income countries. And then we're talking about, so the system is called Panda, as I told you, and our manufacturing line we call it Panda Square, right? All right. A nice project I always want to show real quick. I don't know if internationally it's maybe not that famous, but Puki. These are kids' bikes. So my son, for instance, learned riding a bike on a Puki bicycle. That's why we did this project, to be honest. And then I did not know that Puki bikes are assembled in workshops where disabled people work. So they basically assemble all the bikes. But they have one major problem. They cannot, based on their physical disabilities or mental disabilities, they have major problems with screwing, right? They don't have the proper sensor motor control, so they always hire external workers to finalize the screwing. So what we did, we showed the guys how to use the robot, and the robot is taking over the screwing applications for them now. But meaning this robot is easier to use than a screwdriver, basically. And that is pretty cool. Yeah, quick overview. All these applications you saw, we basically developed them together with our pilot customers. And what is it we actually sell? So I told you we're selling robots, so mechatronics, grippers, and robot arms. But also we are selling the software packages to it, so all these functionalities, like screwing, like inserting, like pick, like place, connecting it to a third device, and so on. And then the third thing, which is the most important, because few people know that, especially those who have no idea in robotics, So the problem with a robot, when you buy a robot at a robot manufacturer, you do not buy a machine, actually. You buy a so-called incomplete machine, which probably none of you has an idea what does that mean. So when you buy, let's say, a vacuum cleaner, there's a CE sign on it, right? And that CE sign means this is a machine that you can take out of the box and take into operation. The problem with these incomplete machines is that you need somebody else to do a risk analysis and all the engineering and programming who will create a so-called complete machine out of it. And what we did is basically by a lot of features and functionality, what we could do, we're actually creating complete solutions which are shipped with the CE sign. So you do not need any third person anymore. You can just take out the robot out of the box and take it into operation, which is quite the advance. And then we have just a quick overview of some customers. We are acting quite internationally. We started obviously in the European Union, but we expanded this year to Asia, especially China and the US, opened an office in both places. But also, as you know, or I think I said, we're a startup. We're 100 people and we have several thousand robots to ship and a lot of customers. So we obviously cannot manage all of them ourselves, and we created a joint venture with that, with a company called Voigt. It's one of the biggest family-owned companies in Germany, or in Europe actually. And when you are in the US or in China or in Japan and you have a problem or you need support or anything, you can basically give them a call. But please leave me out of it. So, real quick about robotics itself. I think that robotics is a mega trend or something that is obviously changing or gonna change our world heavily, is obvious fact, because in countries like ours we have a major problem of shrinking and aging workforces. We don't have people to do the tasks they did before, and we do not have people to take care of the people that are elder or our elderlies. I mean, that's really a pity. We have also the advantage of that in low-income countries we have massive rising labor costs, so it even becomes too expensive. So, you know, Apple does not build a single iPhone themselves. They have contract manufacturers. One major one is Foxconn. They have 1.5 million employees producing smartphones. And you should imagine that China became too expensive now for Foxconn. So they're going to Cambodia, and they're going to Laos, and they're going to Vietnam. But we have major factories with almost 100 million workers working in China. So what are they going to do? And obviously that's why China has this massive plan to automate the entire world. And also that is for us, and not only for us, but all manufacturers of robots, obviously a major possibility. Let's just go over this. It's not so good. About the market real quick, I think two things that you should always, or that are relevant here is actually this one, the pie chart. The dark blue one is automotive industry, right? So that's the market share automotive industry has right now. And what we're going to see over the next years, because we have better robots, we can set them up faster. Obviously, there will be a diversion into other markets. And when you look at these numbers that are coming from McKinsey and Boston Consulting, and they know, obviously, what's going to happen in 10 years. But what is important is that the classical automation industry reached its peak. They're only growing basically because the industry they're serving is growing, so the car industry. But what we're going to see is these new type of machines are going to be the massive amount of expansion. We're talking about roughly 10,000% of market growth, which is quite unbelievable, to be honest. How does it work with us? So we are obviously focused on robotics technology, developing technology for robots. I saw a quick before Ross, 10 minutes? All right, I'm almost done. There's a lot of videos coming, but we're trying to focus always on robotics, and what we're doing, we're basically releasing, let's say, our robots for free, and we're releasing our SDK for free. So basically everybody who's interested can join and create new features, new apps, and new skills for robotic system. And why do we do that? It's because what I said initially, factory assistant, yes, that's today, but it's obvious that, and we are working heavily in such projects, that we are going first, we see it here, in professional service care, so helping those people that cannot help themselves anymore. We have a project, for instance, at Charité University Clinic, where ALS patients, so like Professor Hawkins back in the days, he cannot eat and drink himself anymore, so he gets a robot basically helping to do that. And what is, I think, the most important, I think you are a bit old maybe already, but we're talking about something, the robo-natives. So this generation that will create the new technology of the next 100 years. So what we did here, what we do, we always do robothons, where we have, in this case, it was bachelor students that have never seen a robot in their life, and they had 4 days to solve those tasks, so home assistive tasks, right? Opening a door, making lemon, making coffee, and then obviously setting up everything in my house, and making waffles and all these things. And they did that without any prior experience, and in 4 days, including setting up the end effectors. Of course, it's all prototypically, but this is the level we reached now, that people that have no idea about robotics can now use a real robot and not a, let's say, a toy robot. And then they went to the major fair. These were not even university students, these were school students, and they programmed these tasks. So for instance, giving away little buttons, and showed that at the Ideen Expo, which is a kids fair basically. And if we manage to get as many people and as early as possible onto these technologies, then I think the impact that robotics will have will be maybe multifold bigger than what happened with the smartphones, because this is now real-world applications, right? And not only ending on my computer screen. And then I thank you for your attention. Thank you very much. Questions?
All right, thank you very much, and let's open up the floor for questions. Okay.
Only easy questions, please.
Okay, sorry. That very neat video of yours where your robot inserted the 7 packs of different size. Let's say my production line is faulty and the 7 packs arrive in reverse ordering. What would your robot do?
Could you?
So you had the 7 packs of different sizes which your robot inserted. The smallest one came first, and let's say my production line is faulty, or the packs arrive somewhere, and they arrive in reverse ordering, which the largest pack in front and the other packs. What would your robot do?
So it depends a little bit, but let's say he uses the wrong pack that doesn't fit in the one that you want to put it, whether it's too small or too large. He realizes that he cannot manage it. That's what's going to happen. So basically he will, I go into this, wait. Sorry, real quick, then it's a bit easier to, this one. So basically this interface, the cloud, will then pop up this robot, for instance, that is the one that's in operation, and he will tell you, hey, there's something wrong with my application. And, but obviously these are problems then he can also learn, right? That he doesn't, so let's say there's pegs coming and you have no idea which ones are coming. Obviously it's not maybe 100% meaningful, but let's say there's a pile of different ones coming and he doesn't know which one is he has to use. But theoretically he will even learn how to manage that, but it's obviously maybe not a good way of automating something if it's total chaos. So, but that's the, obviously this question is really good because that's what the skill is, right? That he understands that there's some problem. But obviously from FDIs, from fault detection to isolation, and then what is the recovery or what is my strategy after that? That is something you can basically also set up yourself. So you can give the robot a command, what is he supposed to do? Should he try it for 5 seconds? Should he try it 5 times? Should he just stop and give me a mark? So that's how it is. I hope this answered the question.
First, thank you for the impressive talk. 2 very simple questions. First one, how does the robot know that the smartphone is functioning correctly if it has no camera, because he cannot see that the selfie was correct?
You can also see that in the video. So this is actually so we went to the production and looked how it is working right now, because right now people are doing that. And the people are only the manipulators, not the actual quality checkers. It's really unbelievable. So what you see here, this one. This is the connector to the test protocol. So there's a test protocol attached to the phone, and that's actually checking whether it worked or not. It's not visual inspection.
Okay, thank you. Yeah. And the second one is, do you think it's possible that the robot will change the diaper of a baby, for example? And in how many years will it be possible?
So, I mean, as I said, we are heavily working in those service applications, but actual caretaking, what nurses do, or similar problems, what you're talking about, I think this is for a long time a human task because it's too many variables. What we have the major, so, you know, this object, we have two, for a robot, major differences. We have a stiff object, which is no problem, but what you're talking about are flexible objects, biegeschlaffe Teile. And it's really difficult, and today impossible, to manipulate properly, of course in a single case and show a nice video or something, but that it actually works all the time, it's still, I don't know. If you ask me, I think decades or something like that, but obviously in this time, so we are the manipulators, right? We're not perception guys. We're not heavily focused on let's say, object recognition, detection cameras and all these things. There's still major problems with all devices. They are still not stable enough. It's difficult to calibrate them. So we have a feeling robot now, but what I said, we have this type of feeling, right? The human has two types, this one, and then the tactile in the fingertips, in the skin actually, and that we still don't have, and I think it's a bit far away until it works properly, right? So it's gonna take, I don't know, 10 years, I don't know. I really don't know. More than 5 years is, I think, really difficult to see what's gonna happen. Or, sorry,
Thanks.
you were saying
really cool tech. Yeah. I'd like to learn a bit more about sort of the learning capabilities of the robot. So how much of it is sort of built on classical control algorithms, and how much of it is built on things like reinforcement learning from the machine?
So basically, what you see there is reinforcement learning in general. But so what is the major problem? The major problem is that what we tried a couple of very famous neural networks just to create the model of the robot, the physical model that. Because a normal robot, when he stands still, the brakes are holding it in this position. But we don't have, these types of robots, they don't have any brakes anymore. They have something called gravity compensation. So they are just standing, basically holding, like you hold your arm like this. And with the neural networks, so creating the model that will just keep the pose. We did not manage. The robot fell down all the time. And the problem is that these neural networks, they completely ignore physics, right? And that's the key issue, actually. Because disregarding physics in the real world, I mean, we have gravity and we have weight and we have momentum. These are, in my opinion, it's not possible to solve it without any controllers, without any models. You need to give constraints. Otherwise, it's just not going to work. And you see that in a lot of clips coming a lot from especially from the US, where you see so-called learning whatever, that a lot of things just don't work. And I think it's because they are disregarding physics. That's what is not working. What we saw in the manipulation, the basic controller and the models were running, but learning the task was completely reinforcement learning, basically. Right?
Hi, thanks for the nice talk.
No problem.
I was wondering how much of your control is digital and how much of it is analog? Because a digital control is much more apt to kind of being modified. Whereas, for example,
what is an analog control?
Like, for example, our nerve, where there's no kind of representation of this signal into a digitized manipulable code, but it's really directly the raw signal which generates our reflex. So that would be for me an analog control, whereas a digital control is, okay, I have the torque signal, I compute something out of it, and I generate again an analog control.
Yeah.
So I was just wondering, is there also analog safety modes in your robot? So if I change the code maliciously of your robot, would it still stop?
Ah, okay, okay. So there is a part of the control, and that's the safety, which you will, or if we give you admin access, you would be able to change it. But if you are, as long as you're working because basically how does this work? This type, right? So in this type of programming, obviously you're very limited in functions. You cannot change any functionalities, or especially not the safety. But this is running basically in Chrome. So what you can do then, you can go into these individual apps and also start writing codes actually. But even those codes will not overrule the safety of the robot. There's a third way, that's when you get basically admin access, but then you need to be, so it's not admin at our place, you get it, but then you basically shut down all the safety functionalities. Or you can shut down all the safety functionalities. Yeah.
Thank you. You mentioned that, or from what I take, all of your interaction and all your sensors is basically the torque sensor you have in the motors and the joints. You obviously made a conscious decision not to add any more sensors, and I would just be interested in why not.
I did not say that we do not have more sensors. I just talked about the torque
but
sensor.
you don't have a visual sensor, and you don't have a tactile.
No, we have acceleration sensors, position sensors, temperature sensors, and IMUs mostly. These are the most important, but no visual. No. But basically, as we're talking about here, so we're not programming anything in machine code anymore. We are talking about basically a distributed service architecture. And what you do, maybe we see it somewhere. I think in this one video. So basically, what you can do, you can write your own service, and we give you the templates. Maybe we have one here. No, but in the end, you can write your own service which connects it to a third sensor, for instance, the perception sensor, to give, let's say, coordinates to grasp something, or to give a command to a let's say, second machine, like a conveyor belt that gives a signal. So you can create those services yourself, and it's not really difficult. And you can use any perception sensor, or not any, but most of them.
And that is actually related to what I wanted to ask in the video where it was packing the boxes.
Yeah.
How does it know where the next box is located? Because you only showed once, like where to grasp the box.
Yeah,
but
sorry that I'm jumping here now, but it's always easier to show. This one you meant, right? No, the next one, I think. Those. So what you told the robot is that this is not just one package. You gave him a pattern, and you can do this pattern 4 times 1, but you can also do it circular or square 4 times 4, and then he just knows. And you don't need to program these positions. You just tell him the first one, and then you say there's coming more, and then he will just continue. And you can even use him as this I can show you in this example, as a passive. We call it passive conveyor. So where the robot is actually dragging the workpiece into his own workspace. Wait, I think it's coming after this one. Sorry. Wait. Then it should be after this. I'm sorry. Or maybe it's not in this video. So basically we have, there it is. So basically here we have, let's say, a stack, and the robot drags the workpiece into his workspace, and then he just knows. And those motions, so the problem is, because we have a 6-axis robot, so we have 7 degrees of freedom, and those motions you cannot do, because most robots have 6-axis degrees of freedom, but you can either take it yourself or,
So what happens if you put a pendulum at the end of the robot arm? So
to do what?
Just to see the
scientific
reaction. So actually then you get a torque, so it maybe starts later moving, then the robot arm moves to the left, and then it overtakes it if the robot arm stops, and do a push. So you never tried something like this to
I really did not understand what you're talking about.
Okay.
Sorry.
Okay, so I just think about having
so you have a robot, okay, and he has a pendulum in his hand.
So no, it's moving somehow different than what the robot starts moving it, and then you get an additional torque maybe at the end of the movement.
Okay.
So how
okay. I think what you're actually asking is you're talking about dynamic measuring of the weight, the center of mass actually, because that is. Sorry. So basically, it's a similar problem. Once the robot grasps this, and then he grasps this. This is, I don't know, 50 grams. This is a full glass, 200 grams, right? This is, I think, the question. Is it? No?
No, I think
okay.
So maybe you have a full glass.
Yeah.
So you start moving it.
Yeah.
And the water will get in motion
Yeah, but that's what I mean. The center of mass is changing, and whether the robot can understand that. So with the glass, yes, but there's not too much happening. With the pendulum and, I don't know, 2-3 kilograms, I think it's going to be difficult. But what is possible is, so what we do, how this actually works, for also how are the robots taken into operation? Because today, when you buy a robot, let's say you're a Volkswagen dude and you order a robot, the first thing you do is actually create the model of the robot. You have to do it because the model of it and the actual model are two different things. So the motions are quite bad. So you're tuning this is the first thing you do. But we do this already in the production. And how does this happen? Basically, the robot grasps a 2-kilogram object and he throws it around in his hand. And that's how he understands his center of mass. Right? And you can always do that with an object. When you grasp it, then you can tell, okay, click, and then he's driving around for 20 seconds roughly, and then he realizes how this object is formed.
Okay, so
right?
And he knows what the normal movement is?
Yeah. But if it's constantly changing, I've never tried it, I would say he will take some time until he and then at some point explode or something. I don't know, to be honest.
Next question, I'd say.
So you've shown the thing with the balloon that
Yeah.
it won't
burst. Yeah.
But did you try to grab an egg with your? So because that's also a hard problem for.
So I did
right?
that. So we did this with eggs in our hands and everything. We tried a lot. We did thousands of collision experiments. Yeah. Yeah. Raw eggs, boiled eggs, scrambled eggs. Yeah.
What level of precision can your robots do?
So that's a really important question, because that's the first question every classical automation dude asks. And it's an important question because a classical robot is a stiff machine, so he relies on heavy precision, right? So the entire street needs to be absolutely accurate by micrometers, basically, and then he can manage it because the industrial robots have a repeatability of 0.1 millimeters, right? That's the ISO standard. And we have that, but now comes to the trick question, actually. Why can a standard robot not insert this HDMI cable into the socket? Because there's tolerances always. So the precision is not enough to hit this HDMI cable, except it's exactly at the same position all the time and not even a little bit turned. But why can a human without 0.1 millimeter insert the HDMI cables? Because he can feel. So you have actually a much higher precision. Even though you have 0.1 millimeter precision, you have additionally the capabilities to compensate tolerances, which is really the key issue. Yeah. So 0.1 millimeters, we did that. Yeah. You have to. When you want to sell industrial robot, you have to do these laser measurements, and yeah, we have the same as a classical robot.
Hey, so my question is about the hardware or approach that you choose to...
Could you stand up? Because I don't see you. Ah, yeah. Hi.
Yeah. So what do you think about the approach that, for example, Fanuc chooses to make their cobots, that basically you take an industrial robot that, I don't know, with payload of 35 kilograms and put just rubber skin on it?
So the problem is, and that's why we did these tests, I don't think it's a appropriate approach, in my opinion, because what you see here, again, we're talking about physical moving objects, right? And those robots, they weigh roughly 100 kilos to 1 ton or something. And now we're back to physics, right? You have a mass that is moving, that gets momentum, and even if you have a super fast collision detection, until that 200 kilo robot stops, it just takes time. And that's why we did these experiments, to show even though you're super fast, no way you're gonna beat the momentum in the end, right? You need to stop. And that's why I think it's very dangerous to show those robots without safety fences. It gives a wrong picture about human-robot interaction, in my opinion. Even though those super good robots. But.
Additional questions? Oh, okay, in front.
I think I have the last talk, or? So we have time till tomorrow.
For the robot in my house. So would it be possible to add, for example, a laser cutter attachment or something, so you can actually, or like a CNC attachment, and you actually make it do stuff that other people do, I don't know, in Fab Labs, and basically make this do 5 things that you would need 5 different
that's, yeah, I mean,
machines right now.
That's what I tried to show with this multifunctionality tool. So that is the genius of a robot, that it's not just meant for one purpose, because it's so super flexible. What end effector you attach is up to you. If you want to have a laser sword, or what was your pendulum, that doesn't really matter. But the idea is that you can basically, so I think there was a video, again, sorry, but it's always easier with the videos. So on this, so for instance here, right? I showed a lot of videos with our gripper, but for instance here we have a suction device attached to it, right? And in the end, most devices are just I/O, right, on off. Most of them are super simple. And what it is that is attached to the end effector, as long as it's physically matching, or you build an adapter, and then you have here the Ethercat connection, so basically anything that has Ethernet, so you can connect, doesn't really matter. And you have 24 volts, which is enough for most devices that you need. Right. So now there's a lot of arms again, okay?
Do you think your robot is able to replace a barista in a coffee bar?
So I said before that we started an academy, right, where people come to our place and we have these stations and they learn how to use the robot. And the second academy back in, I think, September, was a guy from the Bay Area who wants to do coffee shops. So I think maybe it's already opened. I haven't been there, but it's gonna happen, yeah. But always, to some extent, right? There's always, so until a robot gets these complex tasks that I can solve as a person, until robots can do that. Somebody asked a question before about diaper changes. These are super complicated things, and we are far away from solving them, no matter what Elon Musk says.
Have you thought about making him move himself, like
mobile
adding wheels or
mobile,
something like that?
So mobile, yeah, basically. So what I said before, we have a 7-axis robot, which is not just one number more. What is the actual problem? It's that you get the so-called null space. It means that you can reach a point in space with different configurations. So the arm can be like this, like this, like this, like this. That's the control problem behind it. If you now attach another, let's say, mobility, right, you get more dimensions. That's actually that's how we want to approach the problem, because we don't want the platform to move independently of the robot, because that's what's happening today everywhere. Robot and mobile platform have nothing to do with each other. Basically, it's like 2 separate machines. And we want to solve these problems always as control problems, as one body that is moving in a certain way. Because even, let's say, the super simple example, you have a linear axis where a robot is attached on the axis and he can drive from A to B, right, to different stations. And what you then see is that it drives, stops, gives a signal, start. And then you have, but if you have let's say this is an 8 degrees of freedom robot in the end, then you would actually, just like you would do it, start already while he's approaching, already have a super smooth motion. And yeah, we're working on these things, but give us a year or 2, then it's ready.
Thank you very much. As we're already at the end of time, I'll have one very last question, and then thank you, and we'll enjoy our dinner.
Hello.
Hi.
So you had a video where you had 2 robots doing stuff.
Yeah.
Have you tried having the robots remove their end effectors and replace them with other end effectors to have more than one step?
Yeah, I can show you that actually. Is it this? No, which was it? So if I show you this, there's a video which I cut actually. No, it's from the. No, it is, I think. Let me check real quick. I think it's in this video. What you see here, you don't really see it very well, but look at what the robot is doing, the right one. He's moving towards the table, and you don't really see it, but what he's doing, he's basically using the levers, pushes them against the table. Where was the person who asked the question? Yeah, hi. So he had a gripper basically in his hand, grasping the joint, right? But you could not grasp the joint with the same gripper. So what he did, he drove against the table, opened the levers. These fingertips fall off. He grasps new levers and then puts them, attaches them again. Yeah, so that's possible.
All right, so thank you everyone. Thank you very much for the talk today. Thank you for all the questions. Enjoy the evening.